Hello everyone, today we'll talk about the solution to the problem split linked list in parts. So if we want to split the linked list into k parts, such that the parts are roughly equal in size, earlier parts are bigger maybe than later parts, then of course we need to know the sizes of the parts that we have. That's because the order of elements has to be the same, so we essentially have to decide when creating the first part, or when splitting the list into parts, at what point to split the first part off of the rest of the list. And for that, we need to, of course, know the number of elements in the list, because if we have the number of elements in the list, that's about how many elements every part, well, that divided by k, is about how many elements every part has, and early parts will have that, but rounded up, later parts that, rounded down. So, as a warm-up, how do we decide how many elements a linked list has? Well, we're going to be operating using head, so the pointer to the head of our linked list. So we'll remember it as old head so that we can later make sure that the head is again the head of the linked list. And we'll be just counting how many times this pointer is not none for every time we increment our counter and move to the next pointer. At some point, since the list has no cycles, we'll fall off the end of the list and we know how many elements that list has. And then we make sure that the pointer again points to the beginning of our list. So that is the number of elements. So what is the size of every portion? Well, we can calculate that size a priori, we can calculate it before running anything, or assuming that we still have to make k parts and we still have n elements, then it's just n plus k minus 1 floor divided by k, and then we can remove those elements from the list, from the number of elements, and subtract the remaining number of parts, subtract 1 from it, decrement it. So how does it work? Well, instead of just calculating n divided by k and then trying to see when we should add 1, when we shouldn't add 1, we can just notice that at every point we have to take the number of elements that remain divided by the number of parts that remain, and since we want the earlier parts to be maybe bigger than later parts, we have to round up. And to round up, if we have this floor division function, because double slash is floor division, then if we divide by k, we can just add k minus 1 to the element that we're dividing. So essentially when you see n plus k minus 1 floor divided by k, this is the same thing as n divided by k ceiling. And feel free to think about why it works. In particular, you can maybe imagine having a number n and n plus 1 times k, everything in between, and whenever you're on this position, you have to round down to the result equal to k. And now when you move up this ladder by k minus 1 steps, this is exactly the same thing as if you were to ceiling divide it. So the result is n plus 1. Well, this of course should be n. And n plus 1. Well, this is a digression. So at any point we can just divide n over k, get the ceiling of that, and that is the size of our part. So our part will always begin with the head of what remains. And now we need to go through the rem size elements and make sure that the last element of our list, of our part of the list, will have its next pointer being set to none. So here we essentially go through the whole rem size, so we decrement it, push the head forward, and remember the previous node that we've seen. And now in that formulation, the previous node is the last node of our part, and the head node is the first node of the remaining part, which may be none. So that prev is the last thing that we still have in our part, so its next should be set to none, of course, if it's not none already. And that is the part that we have added to the result. We do it k times, and that's it. That's the split into k parts. We return the result, and you have solved the problem.